In this video, we'll be discussing Project 5, or the spectrophotometric analysis of a two-component mixture. So just a brief review of the absorbance. Again, the absorbance is actually the negative log of the transmittance, and transmittance is what is measured by the spectrophotometer, which you'll be using microlab. And so the detector measures the amount of light that is transmitted through the sample, and that's converted to absorbance, and then we can use Beer's law to calculate the concentration of a solution. And so in Project 3, you did this with an unknown concentration of protein. In this project, we're going to make it a little more complicated because now we're giving you a mixture that has two different things in it, and we want you to calculate the concentration of both of those. So again, here Beer's law, where absorbance is equal to the molar absorptivity times the path length times the concentration of the solution. And so before, when we just had one substance to worry about, we simply made the known concentrations of solution, then we measured the absorbance. We were able to make a standard calibration and measure an unknown, where then once we had the absorbance, we could get the concentration from our linear regression plot. Now when we have two different things happening, is we'll see that absorbance is actually additive. So I had mentioned previously that molar absorptivity constant is dependent on the substance, and it also is dependent on the wavelength that you're measuring. So if we were to look at something like this, this would be the absorbance plot. So wavelength on my x-axis and absorbance on my y-axis. If I had two different things in solution, so my dotted line here is showing the absorbance of yellow 5. And so it has a slightly higher absorbance at 405 than at 465. And then my yellow 6 dye in the solid line here, which has a slightly higher absorbance at 465 than at 405. And so we can see again that the molar absorptivity, if we just looked at 405, the molar absorptivity for yellow 5 would be higher than the molar absorptivity for yellow 6. And that's basically what that's telling me. So if absorbance is additive, you're going to make the same concentrations that you made in Project 3. Well, you'll make solutions where you'll make known concentrations, and then you'll measure the absorbance. But now you're going to have to make two different calibrations. One for your yellow 5 dye and one for your yellow 6 dye. And then you will make calibrations at two different wavelengths. And so where this comes from, so if we're then looking at our absorbance at 405, using Beer's law, then I know if it's additive, my absorbance at 405 is going to be the absorbance of yellow 6 plus yellow 5. And that's going to depend on the molar absorptivity. So I can write a similar equation for the absorbance at 465, but here what this is telling me is the absorbance at 405 is going to be the molar absorptivity of yellow 5 dye times the concentration of yellow dye 5 plus the molar absorptivity of yellow 6 dye at 405 times its concentration. So you'll be making 4 different calibration plots. As I said, you'll have 2 for yellow 5, one at 405 and one for 465. And then 2 more for yellow 6, one at 405 and one at 465. And so As we mentioned before, if our linear regression is in the form of y equals mx plus b, where y is the absorbance, x is my concentration, then basically my advertivity times path length term is going to be the slope of that linear plot. So you will take the slopes of your linear plots and you can plug them into here. So this is where you'll calculate your EL, and you can plug them back into here. And so this is where the fun really comes in, is that now you'll have two equations and two unknowns. So your unknowns being the concentration of yellow 5 and the concentration of yellow 6, and your two equations is this one right here, and then the same one written for the concentration at 460, or the absorbance at 465. And so then you do a little math and you pop out the concentrations. And then you will know the concentrations for an unknown concentration two-component mixture. The second part of this lab is we will be doing a standard addition calibration. So the first part of this lab and in project 3, you did what was called a standard calibration. And so you took known concentrations of standard, you measured them, and then you took the concentration of your unknown. There could be some drawbacks to this method, is if you're just making up standards, let's say in pure DI water, you're not taking into account kind of the sample matrix effects. And so what if I wanted to measure something in lake water? The ion concentration might be slightly different than it is in DI water, which could kind of skew my absorbance a little bit. And so sometimes the other method that we can use is a standard addition method, in which you prepare your samples similar to how you do for the standard calibration, but in this, you'll always have the same volume of your unknown that you're trying to determine the concentration. Then you'll have some varied concentration of standard, just as we did over here. And then you'll have some DI water to make up the volume, so they're all the same. And so in this instance, your calibration curve is going to look a little different, because when you have 0 standard concentration in there, you're actually going to get an absorbance because you have some of your unknown in there. And so you'll have the same amount of unknown in all of these. You're varying the concentration of your standard. So you can construct a standard addition plot like this. And then you will do a little math that is we're guided through in the materials to calculate the concentration of the unknown. This becomes a little bit faster than the standard calibration, because you don't have to make kind of your standard plots and then test the unknown. You're kind of testing everything all at the same time. This would be a little more complicated if you had a 2-component mixture, and so that's why we're not doing it with a 2-component mixture. We're just doing it with the yellow 6 dye.